Welcome to the very first lecture for DC Circuits, the Central Texas College course CETT 1303. Ignore this 4 on my slide here because this is the PowerPoint that's always been used. Today we're going to be talking about scientific notation, more specifically engineering notation and metric prefixes, because this is what we use to express our values in electronics. We're able to express very large and very small numbers in a very compact way using engineering notation and the metric prefixes that go along with it. We are also going to be talking about charges and voltage and current and resistance, because these are the basic pieces we need to form a DC circuit. And we're going to see what the basis of these pieces are, where they originate, where they come from. So without further ado, let's just go straight on into it. And this scientific notation for electronics PowerPoint that I'm going to be using here is available under instructor notes on your left-hand menu in Blackboard. So you can download it and preview it at your leisure. And so, let me kind of get a couple things set up here real quick and move straight along. Okay, as I said, we are able to express very large and very small numbers by attaching a prefix and moving the decimal point. So basically our starting point will change, our starting point for counting will change depending on what that metric notation is. Now, in scientific notation, you can raise any number to a power of 10, or multiply it by a power of 10, essentially. And we're able to do it for any value, such as, let me throw in a blank slide here, such as 100 is equal to 1 times 10 squared. Okay, as you know, 10 squared equals 100. Count the value of the exponent, and it's that many zeros. So 100 equals 10 squared. The number 10 is 1 times 10 to the 1. The number 1 equals 1 times 10 to the 0. As you know, anything raised to the exponent of 0 equals 1. So 1 times 1 equals 1. And so on. You can go, 1 times 10 to the 6th equals 1,000,000, 6 zeros. So that's basically scientific notation. One of the rules for scientific notation is you are expressing the number from 1 to 10 times 10 to some power. So you wouldn't express 625,000 as 625 times 10 to the 3rd using strict scientific notation, because the rule for scientific notation is you are working in the realm of from 1 to 10. So that would be 6.25 times 10 to the 5th, because you have to move this decimal point over 1, 2, 3, 4, 5 places to meet that rule. Well, in engineering notation, we're not quite as strict. Let me erase this. Engineering notation says we will work from 1 to 999 times 10 to a power of n, where n equals a factor of 3. So 1 through 999 we leave alone. It's 100 through 999. At 1,000, we're going 1 times 10 to the third, and we will go from 1,000 to 999,000. From there, we'll go to 1,000,000. One times 10 to the 6th, and so on. So we always work in factors of 3. 3, 6, 9, 12. 1 through 999 times 10 to a factor of 3. And this also allows us to use the metric terms that are associated with these numbers. Now we'll get to that next slide here. Oops. So our base times 10 to the 0. Then we go up to 1,000. So 1 through 999. At 1,000, we go into the kilo range. By using the kilo, we are able to express this thought. We are able to move the decimal point to the left 3 places and start counting from 1 to 999 again. And instead of saying times 10 to the third, we just say 1 kilo through 999 kilos. After that, we can move up to the megas, and notice there is a case requirement on the metric equivalent. Okay, so kilo, capital K, mega, capital M. So we can express it as 1 meg through 999 meg. Going the other way, less than 1, we can do the same thing. Instead of saying 0.001 or 1/1000th, which is 10 to the minus 3, we're able to call that 1 milli. And you've been using these expressions since you started playing with computers. You know, how many megs of RAM? How fast is your clock? How many gigs is your clock? How many gigabytes is your hard drive? These are all metric equivalencies, so you're not writing out a billion or 900 billion, 1 tera, 10 to the 12th. So a milli, 0.001, can be written as 1 milli. So this is just shifting the decimal point and then adding an indicator of what range you're working in. So once again, negative exponents, you're moving the decimal point, you're moving the decimal point to the left. So 1 milli. Oh, the heck with this part. We're going to get to a little bit more of that right here. Okay, notation and number size. We're starting with the base number of 1. Now that number 1 can be expressed in terms of kilo, mega, kilo, milli, and micro simply by moving the decimal point and adding that indicator, adding that metric equivalent. And you're still talking about a value of 1, it's just compared to the indicator, such as base number of 1, expressed in terms of a mega, 1 million. Well, 1 is 1/1,000,000th of a mega. So we're moving this decimal point over 6 places, as you see here. 1, 2, 3, 4, 5, 6. So 0.000001 mega, you have to add the equivalent, is still equal to a base number of 1. 0.001 kilo, 1/1000th of a kilo, is still the number 1. You're just moving the decimal point over 3 places. Going the other direction, where we are referencing a system based on 1/1000th, the number 1 is 1,000 millis. So we're moving that decimal point from here over 3 places. Same thing on the micro. The number 1 is a million micro. You always have to add the indicator. And you see why there's a difference in case. A milli is a lowercase m. A mega is an uppercase m. Now, why do we go through all this? Once again, if I am going to write on a schematic a million ohms, it's much easier to write 1 mega ohm than it is to write or print a million ohms, or 1 times 10 to the 6th ohms. All right? We work, when we discuss values, etc., we work using the metric equivalents. Okay? If we're going from a smaller unit to a larger unit, it's the way it works. A kilo equals 3 places. Kilo equals 10 to the 3rd. So the decimal point moves over 3 places. So for going from base number of 1 to terms of kilo, you're moving over 3 places, 0.001, just like we discussed before. And always adding the metric indicator there. Okay? Once again, going from a smaller unit to a larger unit, 500 milli. Okay, 500 milli. Bringing it back to the base, you have to move to the left, again, 3 places, because we're going from the smaller unit to the larger unit base. So moving the decimal point over the 3 places, so 0.5 base is 500 milli. Going from a larger unit to a smaller unit, you're moving the decimal place over to the right. So base of 0.125, going from the larger unit to the smaller unit, move the decimal place over 3 places and corresponding to the smaller unit base. So 0.125 from the base is 125 milli. So the number looks physically larger. However, we've got the metric indicator to tell us where we're working here. And I think that's enough on that. So now you know how to express numbers in metric form, and you're going to play with it a little bit, kind of do some of the practice exercises in the books from the introduction. By the way, introduction table I-2 gives you the power of 10 indicator, so from 10 to the minus 12 through 10 to the 12th. It gives you the prefix for each, and it gives you the abbreviations, such as a tera, the abbreviation is T, the power is 10 to the 12th. You already know giga is a billion, so 10 to the 9th, capital G, etc. All the way down through pico, which is smaller than nano, which is 10 to the minus 12th, and a lowercase p. Now, let's start talking a little bit about electricity, because this is DC circuits, and we can't have any DC circuits without electricity. So, what we're going to talk about here in this portion is I skipped for just a second there. Negative and positive polarities. We're going to talk about the structure of an atom and what it contains and how that relates to charges. Then we're going to talk about what makes up a charge and how we measure it. Then, where does voltage come from? What does voltage actually mean? How are we forming voltage? From there, and I don't know why I've got check marks on this page already, we're going to talk about current. Where do we get current? What is resistance? What makes up a closed circuit? If there's time and my voice is holding out, we're going to talk about the direction of current and DC current versus AC current. Where are we getting all this electricity? And then talk about the tools that we use for measurements just a little bit. Alright, so moving ahead. There are four main things we're going to be talking about in this DC circuits class. We're going to be talking about current, voltage, resistance, and power. We're not going to be talking so much about capacitance, inductance, and frequency, because that's not the level of this class. You'll get into a little bit more of that when you get into AC circuits, and that'll relate back to DC circuits. So, capacitors, inductors, and frequency, we won't be talking so much about in this class. By the way, once again, this is your Lesson 1 PowerPoint that you are required to download and familiarize yourself with. It's part of the lesson assignments, so don't forget to do that. Alright, as we know, all material is made up of atoms. Again, going back to 7th and 8th grade science classes. And all atoms are made of electrons and protons. Now, these two particles also are two basic charges. Okay? So, the electron and the proton, where the electron is the smallest negative polarity, negative charge, and the proton is the smallest particle of positive charge. The arrangement of the electrons and protons in a substance determine its electrical characteristics, and you're going to see a little bit more of that as we go through here. And when you have a perfect balance, the equal number of protons to equal number of electrons, you're going to end up with a neutral substance. It is not electrically charged at all, because the negative charge and the positive charge cancel one another out. Okay, so in a perfect world, what we have here is a carbon atom and a copper atom. They have a atomic number of 6 and 29 respectively. That means there are 6 protons in the nucleus of the carbon atom, and there will be 6 electrons orbiting that nucleus. As long as you maintain those 6 electrons and those 6 protons, you have got a balanced unit, and it is a neutral charge. No charge to it whatsoever. Okay, over here in the copper, once again, 29 protons in the nucleus, along with a few neutrons. Neutrons have a neutral charge. They don't do anything. They just add mass. Then orbiting, we have 29 electrons. Once again, as long as we maintain that balance, you have a neutral charge. So, how do we get electrical forces? Well, what we have to do is we have to separate those protons from those electrons. We have to build tension. Once you change the balance of those forces, you get the beginnings of electricity. Now, how does that happen? All right, real quick, we have a battery here. We have a negative terminal. We have a positive terminal. What that means is the positive side has got an excess of protons. You've created an imbalance, and the negative side has an excess of electrons. And now there's a potential between those two, depending on the difference in charge. Now, once again, electrons, protons in an atom assemble in specific combinations for stable arrangement. And of course, that stable combination makes a particular atom. So going back to the let's back up again here. Going back to these two atoms, because of the arrangement of where the electrons are orbiting the protons in the nucleus, that's what makes this a carbon atom. The combination of protons and electrons and the arrangement of the electrons, where they are circling, what ring they're circling the nucleus in, makes this a copper atom. Start shuffling these electrons around, it becomes something different. So here's a quick little bit of the periodic table, though it's not really the periodic table. Silver has got an atomic number of 47, which means there's 47 protons, 47 electrons, and it makes a real good conductor. This number here, the valence number, tells us that it's a good conductor. And in this case, it's a valence of number 1. And that kind of means that the electrons aren't exactly stuck to that atom very well, and they could come loose, which means we can create an imbalance of protons versus electrons. All right, hydrogen atom. It's got a nucleus of 1 proton, no neutrons. In orbit, it's got 1 electron. The weight of this protons are actually a little bit heavier than electrons, which helps create the force to keep this guy in orbit. He wants to go toward that proton, but the forces keep him in a perfect orbit. He's going nowhere. This hydrogen atom is a stable atom. Now you saw in the copper atom and in the carbon atom that each one had different rings, and those are known as orbital rings. The distribution of the electrons determines the electrical stability of an atom. You notice the copper atom that we looked at earlier only had one electron in the outermost ring. Well, because of that one electron in that outermost ring, he's not the most stable of atoms. And, well, in this statement here, electrons in the orbital ring farthest from the nucleus are the most important, because those are the ones that can escape the easiest. They can escape their orbits the easiest. And when they do, they become free electrons. And free electrons create our imbalance in atoms. And when they start moving from one atom to another, they become the basis of electrical current. So once again, out here in the carbon atom, or the copper atom, we have one lone electron. He is not tied to this atom as strongly as the 18 in this other ring here are. He can get bumped. Another electron can come in, get into this orbit, and knock him out. And he becomes a free electron. And he can do the same further on down. He just needs some sort of force to make it happen. Whereas in the carbon atom, carbon is what's known as a semiconductor. It's not a good conductor, it's not a good insulator. You can force these guys free, but it's not as easy as it is, say, with copper. But it can happen. Okay, so when you can knock those electrons free, you got a conductor. Good conductors are silver, copper, and aluminum. And if you look at the valence electrons, that outermost ring is known as your valence ring. So if you look at your electron valence, silver is at a 1, copper is a 1, gold is at a 1. Aluminum, not quite as good as the other ones, but it's still a conductor. Iron, once again, not the best conductor, not something you would want to use in a low loss environment, but it will still conduct electricity nicely. Semiconductors, 4. And of course, because insulators are made up of more than one element, there's no insulator on this table. Insulators are made up of things that do not lose their electrons very easily. Glass, silica, not real easy. Great insulator, glass. Plastic, of course. Plastic is a great, and rubber we also know to be a great insulator. Paper is a pretty good insulator. However, paper can build up a charge. And that charge means that it can store a charge. We call that a dielectric. So a dielectric is a material that is good at storing a charge. Okay, semiconductors we already discussed a little bit about, and you can look at the valence numbers and see them on the table here. We already discussed the atomic number a little bit. The atomic number tells you how many protons, how many electrons. So an atomic number of 6, like carbon, 6 protons, 6 electrons in orbit. Now, the orbital rings, there are levels. Okay, the innermost being the K ring, and if you have multiple rings, the outermost will be the Q ring. The outermost rings, and it doesn't matter if the outermost is Q, P, O, the very last ring can have a maximum of 8 electrons in it. 8 electrons in the outermost ring is a complete ring. You're not going to lose electrons out of that ring if it's got 8. And then the rest of the rings have got varying numbers. Okay, K ring, you can only have 2 electrons in. L ring, maximum of 8 electrons. Now these are maximums. These are not exact. You know, what's going to be in that ring. These are the maximum numbers. The M ring, if it's an outermost, if it's a valence ring, it'll have maximum of 8. If it's not, it can have a maximum of 18. The N ring, well, N ring, outermost, can have 8. Interior, it can have 8 or 32, etc. The Q ring, if there's a Q ring, it is also always the valence ring, and it can have a maximum of 8 electrons. If you have 8 electrons in your outermost ring, you have got a stable atom. You've got an insulator. Okay. Looking again, here's copper. And the copper, you can see in the N ring, we have 1 electron, which would make for an incomplete N ring. What's a complete N ring in this case? Well, it would be 8. However, copper only has 1. With a valence of 1, it's going to be a pretty good conductor. This guy's not bound as tightly as he would be. All right. So, as I keep saying, the maximum number of electrons in the outermost ring is 8. It is your valence ring, and the electron valence of an atom is the number of electrons in an incomplete outermost shell, and it will indicate how easily you can gain or lose electrons. And we're not worried about neutrons, so we're going to move on, and we've seen this one before. So now we've got all these electrons that we're able to knock loose of our conductors, and if you have enough loose electrons, you have the value of a charge. So what is a charge? Well, a charge is 6.25 times 10 to the 18th electrons or atoms heavy in protons, which means they've lost an electron. My train of thought derailed for just a moment. All right, so a charge is measured in coulombs, named after Charles Coulomb, which is a great bit you can read in your book. So 1 coulomb of charge is equal to, as I said, 6.25 times 10 to the 18th power. This can either be negative charge, so heavy on electrons, or positive charge, heavy on protons. The symbol for the charge is Q, for quantity. The value is coulombs, C. So you would say the charge is equal to 1 coulomb. So this is the symbol you use for your formulas. This is what you use for the value of 1 charge. 1 coulomb of charge. Okay, as I said, you can have positive charge or negative charge. So a positive Q or a negative Q of a charge. Charges of the same polarity, just like magnets, they're going to repel each other. Opposite charges are going to attract each other. I mentioned earlier that protons tend to be a bit heavier than electrons. The fact that they are a bit heavier, which means they've got a little bit of a gravitational well to them, and they are positively charged, they are going to attract electrons. So electrons are going to go toward the positively charged protons. And as far as the rest of it here, we've already talked about this. So we're going to move right along. All right, here's your graphic. Opposite charges attract, like charges repel. So the charge of an electron, well, the charge of a single electron, or the Q of an electron, is 0.16 times 10 to the minus 18th C. That is the charge value of a single electron. Now that would actually be a negative Q of an electron. See, it's indicating Q of an electron, because of course electrons are negatively charged, whereas a proton, the charge of a proton, is equal to the same value, but it's positive. It's a positive Q because obviously protons are charged positively. In all my life in electronics, I've never had to think about the charge of a single electron. But it's good to know that it's there. Alright, so now we have the value of a charge. We know how many electrons it takes. A lot. Billions and billions. Now we have to be able to do something with that. Well, this is where the volt unit comes in. Now, potential difference refers to the possibility of doing work. So you take your 9-volt battery. Okay, let me bring this in. Your basic 9-volt battery here, where one end is positive, it has an excess of protons. The other side is negative, it has an excess of electrons. Because I have these two charges available, I have the potential of being able to do work. And of course this is 1.5 volts, so I have 1.5 volts of potential energy in here. Okay, we'll get rid of that. So, any charge has potential to do work of moving another charge, either by attraction or repulsion. And when you have two unlike charges, you have a difference of potential, referred to often as just PD, although I usually use the whole words myself. And the volt is a unit of potential difference. Okay, so we also call that voltage. Now, what is voltage? Where do we get it from? Well, we have to be able to measure the amount of work, or the potential to do work. And that's where work energy comes in. The joule is a measurement of work energy. How much energy is expended to do a fixed amount of work. So 1 joule is equal to 0.7376 foot-pounds. So if I exert that many foot-pounds of energy to move something, I've done 1 joule, or I've expended 1 joule of work energy. Excuse me. So now potential difference, or voltage, between 2 points is equal to 1 volt of potential difference when you expend 1 joule of energy to move 1 coulomb of charge between 2 given points. And the formula for that is 1 volt is equal to 1 joule over 1C, or voltage is equal to work, small w, over charge. So a 9-volt battery, as shown here, has the potential of expending 9 joules of energy per coulomb of charge moved. And that's voltage. The ability to expend energy moving a charge. Now, how do we get potential difference? Or what is potential difference? Does the kind of charge or the amount of charge matter? Well, here we have various charges. In this case, we have a plate that's heavy on protons, so it's a positive charge, positive 1C, and it is being worked against another charge of positive 3C. So both of these charges are heavy on protons. However, this one is less heavy on protons. It has more electrons than this one. Well, the difference between the two is simply 2C. 1C, or 3C minus 1C. Over here, we have an almost neutral charge, 0 C's, versus this plate that has positive 2 C's of charge, heavy on protons. But the result is still 2C of charge. Over here, heavy on electrons, minus 1C of charge. Over here, heavy on protons, plus 1C of charge. Still, the result is a 2C difference in charge. So, it is actually kind of transparent to us because all we're concerned with is the fact that each of these has got a difference of 2C charge. 2C of potential difference. Now, if you apply that difference across another charge, and you cause that third charge to move, that charge in motion is now current, or amperage. Current is the continuous flow of electric charges, such as electrons. Now let's see if we got, there we go. So now we've got a potential difference here, and this is a symbol for a battery, by the way. This is a single cell battery. We apply that potential difference across a copper wire. Now what do we know about copper? Copper can throw off electrons very easily. You just need the force to do it. This potential difference, or the voltage, is the force to do it. What do we also know about charges? Like charges repel, difference in charges attract. So we have all these electrons which are negatively charged, and we apply a negative charge at this end. What's that going to do? Well, it's going to repel all of these free electrons, and they're going to act like ping pong balls in a tube. They're going to bump up against each other, going in the same direction, and force them in that direction. At the same time, we're applying this positive charge over here, which is going to do what? These guys are negatively charged. This is a positive charge. So negatively charged items will be attracted to the positive charge. Number one, by the force of the charge. Number two, by the weight of the heavy protons of the positive charge. So not only are they being forced by the negative charge on this end, they're being attracted by the positive charge on this end, and we have current flowing from negative to positive. And current will always flow negative to positive. The basis of the way we work DC circuits in this course is that of electron flow. And electron flow always goes negative to positive. There's another philosophy of conventional flow, which we'll get into in a bit. But right now, electron flow goes from negative to positive. So we have two charges, the negative and the positive, acting on a third charge, this piece of wire, which is the electrons aren't going anywhere until we influence them with these two charges. And we create current flow. The greater this potential difference, so the more voltage we apply, the faster the flow, or the more current we get. So current and voltage are directly proportional to one another. Okay, and we just talked about that. All right. Current is defined as the rate of flow of charge through a single point. Okay, the unit of measurement is the amp. The symbol is I for intensity. You have 1 amp of current. 1 amp of current when you have one charge, 1 coulomb of charge, flowing past a given point each second. So 1 amp equals 1 C per second. Or current is equal to charge over time in seconds. Okay, so you can see the formula given here and the values for that formula shown there. There is a difference between the values and the symbols. That is, when expressing. Okay. Now the last part we need to make a complete circuit is some resistance. Okay, we now have potential difference. We have a path for current, that's the piece of wire. Now we need resistance, because the thing about current is, you're actually moving particles within the piece of wire, within whatever conductor you're using. If it is unrestricted, you have an unrestricted flow. You have very fast flow. Particles rubbing up against each other at a high rate create heat. That heat, of course, unrestricted, will burn things up. So you need resistance. And resistance is the opposition to the flow of current. Of course, we create a component called a resistor. A resistor is usually made out of some sort of semiconductor that you can build for a specific controlled rate. And the formula for that is in the book, and I'll let you go ahead and look that up as part of your reading. So conductors have a very low resistance. Conductors have a very low resistance. Where insulators have an extremely high resistance. So not going to get any current flow through an insulator, which is why we wrap wires in insulators. The unit for resistance is the ohm. The symbol is omega. The formulaic symbol for resistance is R. So resistance is equal to so many ohms. That's how we would express it. And then Your B here is your schematic symbol for a resistor, where your A here is actually a power resistor. This is a wire wound resistor in a cement case. It is meant to work with very high power ratings. This one is a 10-watt resistor. It is 10,000 ohms, 10K. 10 times 10 to the third, or 10 kilos. It's 10,000 ohms. It's just an example of one kind of resistor. Chapter 2 goes into a lot of resistors, and we'll get to that when we get to Chapter 2 next time. All right, now we have the ability to have a closed circuit, a complete circuit. And a circuit can be defined as a path for current to flow. Got to have three things. You got to have potential difference, or voltage. Without voltage, you don't have the force to create the free electrons to create current. There has to be a complete path for current to flow. So you got to have that wire. You got to have that third charge. And that current path has got to have a resistance, either to limit the current or to generate heat, to do something with that excess heat that the current is creating. When we have a closed circuit, we can have a couple of failure modes: an open circuit or a short circuit. An open circuit is a current path that is broken. Incomplete current path, broken wire, open resistor, something that's going to keep the electrons from being able to flow from negative to positive. When you have a closed path, but you got little or no resistance, that's a short circuit, which means you're going to have too much current, free flow of current, and you're going to create excess heat. Burn something up. Okay, here's a typical complete circuit. You've got a positive terminal and a 9-volt. I can never remember which one's positive and negative. So we're going to just call this one negative and this one positive for right now. You have a complete path, so you have the wire for current to flow. You have a resistor to limit the amount of current, and then you have the other end of the wire to allow the complete path for current flow. And here is a schematic of what we see here. You have the battery, and it's a multi-cell battery. The large plate indicates the positive side, so I guess I got them wrong. The large plate indicates the positive side. The small plate indicates the negative side. So current is going to flow like that. So this is a very basic schematic here. Okay, an open circuit, you have no connection. All you have is potential difference. If you measure here and measure here, you're going to measure just the voltage of the battery. If you put a current meter in, you're not going to get any current flow. A short circuit, which they didn't give me, would be straight across. No resistance, free flow of current, and either the wire or the battery heats up and you have catastrophic failure. Speaking of which, let's see here. Speaking of catastrophic or near catastrophic failure, here is a battery that got shorted out this morning, as a matter of fact, and you see the casing on it is split, Had it gone any longer, it would have started leaking and possibly started smoking. So it got very, very hot. All right. We've talked about the direction of current. Current flows from negative to positive. That's electron flow, and that's what we're going to work off of in this class. Now, conventional flow is considered the motion of positive charges. So it flows the opposite way, and that is also the way most schematics are drawn out these days, where you'll have an input, some outputs, and it'll usually end up in ground. And they consider current flowing that direction toward ground. So positive to negative. And here's a graphic for each. Doesn't matter what side they actually draw the labels on. So electron flow from negative to positive. Conventional flow from positive to negative. Here we draw the negative terminal at this end, so that's electron flow, whereas this side is conventional flow. Once again, this class is completely electron flow. Now, this class is DC circuits. DC circuits, current flows in one direction from negative to positive. Alternating current, or AC, that say your house uses, reverses direction on a regular interval. So that interval in American households is 60 cycles, or it will cycle 60 times per second. Okay, and that is measured in frequency. That is, we measure it in hertz. So 1 hertz is 1 cycle per second. And let's see if we got a picture on the next page. There we go. This is a complete cycle of AC right here. So this happens 60 times every second for American households. On aircraft, it happens 400 times per second. But this is 1 cycle of AC power. Over here we have DC. If you put a scope on a DC voltage line, it's going to maintain a single level, and not the way I just drew it there, but it's going to maintain a single level all the time and not change. You put an oscilloscope on a AC signal, and this is what it's going to look like, because the voltage is going to vary as it cycles through as it cycles through the cycle. So periodically your positive becomes your negative, then your negative becomes your positive. All right, sources of electricity. Where do we get electricity? Well, we can separate the electrons and the protons by various means. We can do it mechanically, like a generator does. We can do it chemically, like a battery does. You can do it through photovoltaic cells, and that's the photoelectricity, or photoelectric cells. Photovoltaic, photoelectric, those terms are interchangeable. But a solar cell takes light energy and creates electricity. Electromagnetics, motors and generators. We already talked about batteries being a chemical reaction, or friction, static electricity. As you will read in your book, a lot of experiments were done earlier before anybody thought of electricity, and that's how we came up with the thought of charges and separating electrons and protons just by the different materials you're rubbing against each other. One will want to attract electrons, one will want to attract protons. Then you're able to put those two materials next to each other and they start attracting. So all these laws came out of the 1700s before they even thought about electrical power and use of electricity. So static electricity, you're walking across the carpet, your body's picking up all these protons because your rubber shoes tend to attract protons versus electrons, and then you get near something that's a ground, doorknob or whatever, and you'll get that brief spark, pain in the hand, but the bright blue spark, that is the current. You're creating a difference in potential in your body versus the grounded object, and when you get too close, the air becomes that third charge. So the difference in charges between the grounded object and your body is acting on a third charge in the air, and that's where you get the spark. And that spark, the current, is actually traveling from the negative side up to your body. So that's pretty cool. All right, where the heck are we? See, my voice is starting to go, and we're almost done. How do we measure this kind of stuff? Well, we use multimeters. Now, here we're showing the digital multimeter, and let me bring my meters back in again. Here I have two different multimeters. I have a digital right here. These are my personal ones. And we have my very old analog mechanical movement multimeter. Now these meters will do voltage, current. The voltage they'll do is AC and DC. They'll do current for AC and DC. They will measure resistance. They're handy tools. And one is not necessarily better than the other. They both have their uses from different times. So they're both set for resistance right now. And just for instance, I'll short out my my multimeter here, my analog, and you can see immediate needle movement, an immediate reaction as soon as I touch it up. Versus my digital multimeter that I'll touch it up and there's a little bit of a delay. So there are times when you want to see a needle move immediately versus times when you're just making a measurement and you have time. And that's where the differences between the two come in. Sometimes you need that needle deflection, sometimes the digital works just fine for you. In this case, there we go. In this case, we have a benchtop model that will make several different measurements. Here we have DC volts, AC volts, amps, AC amps, resistance. It will measure diodes and frequency of a AC signal. So the benchtop model can do a lot of stuff. The handheld, the Fluke, which is very common everywhere in the world for any kind of technician. It will also do quite a few things, such as volts, millivolts. This is AC volts, millivolts, DC volts, DC millivolts, ohms. It'll measure your diodes. Looks like this one will do temperature also. Then current, amps, milliamps, microamps. So quite a bit. So these are just a couple of the common tools we use. Though we won't use them too many times in this class, I will be doing a few demonstrations using my own. And that's about all there is to the first part of this course. as far as this lecture goes. Now next time we're going to be looking at resistors and resistance, color codes, different types of resistance there are out there, and we're just going to hit that briefly because we're going to do chapter 2 and we're going to start into chapter 3 where we actually get to start working with Ohm's law and making the calculations that we need to make as electronics technicians. So, and believe it or not, the calculations, the mathematics that we do in this course is the sound foundation for everything. Because as fun as it is to use the test equipment and make the measurements, these measurements mean nothing without having the math background to determine what you're measuring is correct. So that's where we are in this course. So I will talk to you next time. You have a good week, and if you have any problems, anything any kind of questions, be sure to contact me. Don't sit and wait. Contact me as soon as you can, and I will get back to you, I promise. So y'all be good. I'll talk to you later. Goodbye.